In the last video we talked about Riemann sums and we evaluated a definite integral through the use of Riemann sums. We evaluated a definite integral graphically through the use of geometry, and we evaluated it analytically through the use of tables, and now with the fundamental theorem of calculus we can actually determine the value of the definite integral algebraically. So if we have little f and big F as continuous functions, such that big F is the antiderivative of little f, or vice versa would be that f is the derivative of, or little f is the derivative of big F, then all we have to do is say that the integral, the definite integral from a to b, is equal to capital F of b minus capital F of a. So the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. Okay, so let's walk through a couple examples with this. In the first example, so we first have to determine the antiderivative of this function. Well, back in Module 4a, we got some practice with this, so we increase the power by 1, so that's x cubed, and then we divide by that power, so it would be 3 divided by 3. Okay, so just x cubed. Do the same thing here, so we increase the power by 1, and then we divide by that power, and so I just end up with x cubed minus x squared over 2. And then I now need to evaluate this, and I'm going to use a vertical bar, evaluate it at upper bound of 4, and then lower bound of 1. So going ahead and doing this, I get 4 cubed minus 4 squared over 2. And then from this I subtract, now this is the first part, and now I'm doing the second part, so I need to substitute in 1 and see what I get out. So that's 1 cubed minus 1 squared over 2. And so doing this computation, I ended up with 55.5. Okay, so this entire integral is exactly equal to 55.5. Now we repeat that same process down here. So we have to first think about what is the antiderivative of 4 over x. Well, remember, I could write this as 4 integral 1 to e of 1 over x dx. Okay, using the basic properties of integrals that we discussed last time. And so then I have 4, and this is the derivative of the natural log function, so my antiderivative is natural log of the absolute value of x, and then I evaluate this from 1 to e. So I stick in e first, so that's 4 ln of e minus, and then I subtract whatever I get out when I put in 1, so natural log of 1. And this one's a little more straightforward. Natural log of e is 1, and then natural log of 1 is 0. So my answer is just 4. Alright, pretty helpful tool. And again, this is the fundamental theorem of calculus part 2. And so a direct result of this comes into play when we use physics. And so displacement is just going to be what you would get out normally. So you don't have to worry about any signs or anything like that. You just determine the antiderivative of v of t, which is the position function, s, and then evaluate it at the upper bound minus whatever you get out when you evaluate it at the lower bound. Okay, total distance traveled. That's a little bit more intricate. So total distance traveled is the absolute value of the areas. So in essence, and this is the same graph that we saw maybe in an earlier video, so in essence we have the upper areas, the areas above the x-axis, and we have the lower area. And what this says is, for total distance traveled, we need to determine the, we take all the positive areas, okay, and add the area of the lower one without subtraction signs. So we treat a negative area as a positive area. So in essence, the integral here, and we need to split it up. So normally we would do the integral from 0 to 5, absolute value of v of t dt. But now it's best to actually break this up into the positive areas and the negative areas. So we're going to have the integral from 0 to 1 of v of t dt, and then absolute value of that, which it already is positive, so it's kind of redundant. And now we're going to add that, the absolute value of the area from 1 to 3, v of t dt. And then finally we're going to add the integral from 3 to 5 of v of t dt. Okay, so computing this, we can actually do this, since it's defined geometrically, we can do it geometrically. This is going to be 1/2, and then this one is going to be the absolute value of, well, this area technically would be a negative area, but again, since it's absolute values, it's going to be the absolute value of -1. And then finally this one is just going to result in an area of 2. So then I get 1/2 plus 1 plus 2, and I end up with 3.5 as a result. So the total distance traveled is 3.5 and whatever the units are. So total distance traveled. Okay. Basic rundown on the fundamental theorem of calculus and evaluating these different indefinite integrals algebraically.